Chapter 1. How an Iron Box Became King of the Ocean. July 2006, the Aleutian Islands. The car carrier Cougar Ace is slowly rolling onto its port side. Not 5 degrees, not 10, but a full 60. The bridge hangs just meters above the ocean spray. The crew is being evacuated by helicopter. And while rescuers watch the listing vessel from above, inside it, in the darkness of tilted cargo decks, in complete silence, 4,812 brand-new Mazda automobiles are suspended at an angle that no ship was ever supposed to reach while still floating. Nobody knows what is happening to them, whether they broke free from their lashings, punched through the bulkheads, or collapsed into a heap of wreckage. That question can only be answered once the ship is upright again, and getting it upright will take weeks. This moment, a $100 million cargo hanging at 60 degrees in the North Pacific, a salvage crew boarding a vessel that looked like it was about to finish the job of capsizing, is where the real story of car carriers begins. Not because it was the worst thing that ever happened to one of these ships, but because of what the people who entered those holds discovered when the ship was finally righted. What they found changed the way engineers think about these vessels, and understanding what they found requires understanding what car carriers are, where they came from, and why the physics of their design makes them unlike anything else in the commercial fleet. For most of the 20th century, if you wanted to move automobiles across an ocean, you faced a problem with no elegant solution. Cars are precision objects with painted surfaces, glass, rubber seals, and mechanical components that respond poorly to being swung through the air on a crane hook, dropped into a hold, and stacked under other cargo. The first attempts to ship cars in volume produced predictably poor results: scratched paint, bent panels, broken glass, and furious customers at the receiving end. Various workarounds were tried: wooden cradling frames inside standard cargo holds, modified bulk carriers with reinforced decks, purpose-built vessels where cars were lowered through hatches by crane. None of them worked well enough at the volumes that the post-war automobile industry needed. Those volumes began growing dramatically in the late 1950s and early 1960s, driven by something that had not existed before: the Japanese automobile export industry. Toyota, Nissan, and Honda were producing cars in quantities that far exceeded domestic demand, and the logical next step was the American and European markets. The challenge was not manufacturing, the Japanese had mastered that, but logistics. Getting tens of thousands of cars across the Pacific every month, intact and economically, required a method of ocean transport that simply did not yet exist. The solution, when it came, was almost absurdly simple in concept. What if the car just drove onto the ship? Instead of lifting vehicles vertically with a crane, you build a ramp at the stern. Vehicles roll on under their own power and roll off the same way at the destination. The concept had military precedents. Landing craft had been using similar principles since World War II. But applying it to commercial shipping required rethinking the entire internal geometry of a cargo vessel. You needed flat, open decks with clearance for a car, internal ramps connecting those decks at different levels, and a hull wide and stable enough to support the whole arrangement in open water. This concept became known as ro-ro, from roll on, roll off, and the first purpose-built ro-ro car carriers emerged from Japanese shipyards in the late 1960s. The results were transformative. Loading time dropped from days to hours. Damage rates fell sharply. The cost per vehicle transported fell with them. By the early 1970s, virtually every major Japanese automaker had committed to this method of export, and shipbuilders were developing increasingly large and capable vessels to meet the demand. Through the 1970s and 1980s, car carriers grew in size, capacity, and sophistication. By the 1990s, the largest vessels were carrying 6, 7, 8,000 vehicles per voyage. By the 2000s, the biggest ships in the fleet could carry more than 10,000. Today, according to data from the United Nations Conference on Trade and Development, car carriers collectively move around 20 million vehicles per year, roughly a third of all new cars sold globally. But as the ships grew, a problem that had been manageable at smaller scales became impossible to ignore. Maritime logistics researcher Martin Stopford, in his book Maritime Economics, identified car carriers as one of the most technically demanding types of commercial vessels, and the reason he gave was not propulsion technology or navigation systems. It was something more fundamental: the relationship between where the cargo sits and where the ship's center of gravity needs to be to stay stable. On a conventional bulk carrier or tanker, the cargo is deep in the hull, below the waterline. This naturally places the center of gravity low, which gives the ship strong resistance to rolling. The technical term is metacentric height, and a high value means the ship strongly wants to return to vertical when pushed sideways. A fully loaded oil tanker in heavy weather behaves with relative composure precisely because its mass is where it should be, low and stabilizing. A car carrier works in the opposite way. To maximize the number of vehicles on board, designers stack them on multiple decks that extend high above the waterline. A modern large car carrier has 12 such decks, reaching the equivalent height of a 15-story building across 300 meters of hull. The total cargo can weigh tens of thousands of tons, but instead of sitting below the waterline, that weight is distributed upward across all 12 levels. The center of gravity is elevated, which reduces the ship's natural resistance to rolling and makes it more susceptible to the forces that the ocean applies to its hull. Those forces are amplified by what engineers call sail area. The sides of a car carrier are essentially enormous flat walls, rising 40 or 50 meters above the water. When a strong crosswind strikes these walls, the lateral force can exceed several hundred tons. On a deeply loaded tanker, this force is working against a hull that is submerged and dense with cargo, with a low center of gravity that strongly resists rolling. On a car carrier, it is working against a hull that sits relatively high in the water, with a center of gravity already pushed upward by the cargo stacked on 12 decks above the waterline. The combination is why car carriers have historically been more vulnerable to dangerous rolling in severe conditions than other vessels of comparable size. The people who designed the first generation of ro-ro ships understood this in general terms, but the analytical tools needed to model it precisely, real-time computational fluid dynamics, detailed finite element structural analysis, the sensor systems that would eventually allow continuous monitoring of hull behavior at sea, either did not exist or were not yet applied to this problem. Ships were designed conservatively, tested in scale models in wave tanks, and sent to sea. What the calculations missed, experience revealed. And in 1987, experience delivered a lesson that the entire maritime industry could not afford to ignore. The Herald of Free Enterprise was not a pure car carrier. It was a passenger and vehicle ferry operated by the British company Townsend Thoresen on the Dover-Zeebrugge route. But its structural logic was the same as a car carrier. Open vehicle decks positioned high in the hull, roll-on access through large bow and stern doors, a center of gravity elevated by the vehicles and passengers it carried. On the evening of March 6, 1987, the Herald departed Zeebrugge with 459 passengers and crew and a full load of vehicles. The bow doors, through which vehicles had loaded, had not been closed. The crew member responsible for closing them had fallen asleep in his cabin before the ship departed. The officer responsible for confirming hull integrity before departure had assumed the doors were shut. The captain on the bridge had no indicator system to tell him otherwise. As the Herald cleared the harbor and increased speed, water began pouring through the open bow doors onto the vehicle deck. The deck flooded. The ship heeled rapidly to port. Within 90 seconds of the flooding beginning, The vessel capsized in shallow water just outside the harbor entrance. 193 people died. Professor David Keeling, who examined the Herald disaster in detail in his work on maritime safety culture, made a point that has since become foundational in discussions of maritime engineering. The open bow doors were the trigger, but the cause was the absence of any technical system that would have made the trigger impossible to pull. There was no automatic door closure confirmation. There was no indicator light on the bridge. There was no procedure requiring positive confirmation of hull integrity before the ship increased speed. The design assumed that the right things would be done by the right people at the right time. And when that assumption failed, as it eventually fails in any system that relies entirely on human reliability without a technical backstop, the consequences were catastrophic and irreversible. The regulatory response to the Herald unfolded over the following decade, driven by the International Maritime Organization. New requirements were introduced for passenger ro-ro vessels, stricter stability standards, mandatory hull opening indicator systems on the bridge, tighter procedural requirements for departure checks. These changes improved the safety of passenger ferries considerably, but they addressed a specific category of vessel in a specific type of operation, and the broader question of how car carriers, growing ever larger and carrying ever more cargo, would behave under the kind of extreme conditions that the ocean occasionally produces was not fully confronted until the Aleutian Islands, July 2006. The Cougar Ace was operated by Mitsui OSK Lines, one of the largest shipping companies in the world. The vessel was on a standard Pacific crossing from Kobe, Japan, to Portland, Oregon, carrying 4,812 Mazda vehicles, new models of the Mazda 3, Mazda 6, and CX-7, worth approximately $100 million. Everything about the voyage was routine until the crew began a ballast water exchange in the open ocean near the Aleutian chain. Ballast water exchange is a procedure required by international convention. Ships carry water in large tanks inside the hull to maintain stability when the cargo hold is not fully loaded. Without ballast, a lightly loaded car carrier would ride too high in the water, exposing those enormous flat sides to wind and reducing its stability. When a ship transits between ocean regions, it is required to exchange the ballast water it is carrying for fresh ocean water from its current location to prevent the transfer of marine organisms and invasive species between ecosystems. The procedure involves pumping out the old water and pumping in new water, and it requires careful management of which tanks are emptied and filled in what sequence. If the tanks on one side of the ship are drained before the corresponding tanks on the other side are refilled, the ship loses the lateral symmetry of its ballast weight. The resulting imbalance creates a list, and if the imbalance is large enough or the response is too slow, the list can develop faster than the ship's systems can correct it. According to the American Bureau of Shipping's investigation of the Cougar Ace incident, this is what happened. The exact sequence of events has been debated in technical circles since the investigation, but the outcome is not in dispute. At some point during the ballast exchange, the weight distribution became asymmetric. The ship began rolling to port, and by the time the severity of the situation was fully recognized, the angle of heel had passed the point where normal corrective measures could stop it. The Cougar Ace continued rolling until it reached 60 degrees and stabilized there, an angle at which the port side of the hull was nearly horizontal, almost touching the water surface. The 23 crew members were evacuated by helicopter over the course of several hours, in conditions that the subsequent investigation described as hazardous. One person, a maritime emergency specialist who had been part of the response team, died during the evacuation when he fell from a rope ladder. The salvage operation that followed was led by Titan Salvage and lasted several weeks. Their team worked inside a vessel that was effectively lying on its side, carefully managing the controlled refilling of ballast tanks on the high side of the ship to gradually return it toward vertical. The operation required working in enclosed spaces, where every surface that should have been a floor was now a wall, where fluids had migrated to the low side of every compartment, and where the structural loads on the hull were far outside normal operating parameters. It succeeded. The Cougar Ace was brought upright, steamed to Portland under its own power, and eventually returned to service after extensive repairs. But the moment that changed how engineers think about these ships came when the salvage team first entered the cargo holds after the vessel was righted. Every person who entered those holds expected devastation. The reasoning was straightforward. At 60 degrees of heel, every car on the portside decks would have been hanging almost vertically from its lashing straps, supported entirely by the 4 textile bands connecting it to the deck. The forces involved were far beyond what the straps were specified to handle as a routine load. In a fully loaded hold where cars are parked with 10 centimeters between bumpers, the failure of a single strap could send a 2-ton vehicle sliding across the tilted deck, striking the car beside it, which would strike the next, which would strike the next. A chain reaction in a closed steel room with no way to stop it. What they found instead was all 4,812 cars still in their assigned positions, tilted at 60 degrees, because the ship was tilted at 60 degrees. But not one had broken free. The lashing straps had held loads that no specification had ever required them to hold, for a duration, more than 2 weeks, that no specification had contemplated. The vehicles were not undamaged. Many showed evidence of having shifted against their straps, causing dents and paint damage, and fluid leakage from the extended period of listing had contaminated a significant number of engines. Roughly 800 vehicles were eventually declared total losses. But the structural catastrophe that everyone had anticipated, the cascade of freed vehicles destroying decks and hull plating, had not occurred. The engineering community's response to this discovery was not simple relief. The straps had held, but nobody had calculated that they would. The margin of safety that had saved the cargo was not a designed margin. It was an accidental one, the product of conservative materials specifications and careful installation practice accumulating into a reserve of strength that had never been formally quantified. The question this raised was uncomfortable. What if the list had been 65 degrees instead of 60? What if the straps had been installed slightly less carefully on that particular voyage? What if the sea state during the list had caused additional dynamic loading on the vehicles? The answer to any of these questions might have been very different, and the industry had no rigorous basis for knowing where exactly the line was. This gap between assumed safety and understood safety drove a substantial revision of how car carriers are designed, loaded, monitored, and operated. Ballast water exchange procedures were redesigned with additional safeguards and sequencing requirements. Lashing specifications were reviewed and tightened. Onboard stability monitoring systems were upgraded. The analytical models used to assess car carrier behavior in extreme conditions were refined using data from the Cougar Ace incident itself, which provided a set of real-world observations at parameters that no controlled test would ever have generated. All of these changes addressed specific, identifiable vulnerabilities that the incident had exposed. But they also pointed toward a deeper engineering challenge that no single regulatory change could fully resolve. A car carrier is a structure whose stability depends on a constantly shifting combination of cargo weight, ballast water, sea state, wind loading, and hull geometry, and managing all of these variables simultaneously in real time in the middle of the ocean requires systems of a complexity that the first generation of ro-ro designers could not have imagined. How those systems work, and what it actually takes to keep a floating 15-story parking garage upright when the North Atlantic is doing everything it can to tip it over, is a story that begins not on the bridge or in the computer room, but deep inside the hull, where the ship's ability to reshape its own geometry in response to what it is carrying turns out to be the foundation on which everything else depends. Chapter 2. How an iron box stays upright. Take a 15-story building, lay it on its side, stretch it to 300 meters, fill every floor with cars, and then ask it to balance itself on moving water while a storm pushes against its walls with the force of a freight train. This is not a metaphor for what car carrier engineers face. It is a reasonably literal description of the problem, and the reason it took several decades of accumulated failure, near misses, and one spectacular capsize in the Aleutian Islands to fully understand the solution is that the problem turns out to be considerably more complex than it looks from the outside. The difficulty is not static. It shifts constantly because the thing that determines whether a car carrier stays upright, its center of gravity, is not a fixed property of the vessel. It changes every time a different mix of cargo is loaded, every time a ballast tank is filled or emptied, every time a wave pushes against the hull from a new angle. A ship that is perfectly stable leaving the port of Kobe might become dangerously unstable halfway across the Pacific if the ballast management system makes the wrong decision at the wrong moment. Understanding how modern car carriers manage this moving target requires going back to the point where the industry first confronted how little it understood about the problem. Through the 1970s and early 1980s, as car carriers grew larger and more numerous, the approach to stability was essentially empirical. Ships were designed using established naval architectural principles, tested in scale models in wave tanks, and sent to sea. The feedback loop between design and experience was slow. It took years for the operational patterns of a new vessel class to produce enough data to reveal systematic vulnerabilities, and the analytical tools available for studying hull behavior in extreme conditions were limited by the computational power of the era. Designers worked with conservative safety margins and hoped those margins were sufficient. Sometimes they were not. The events of 1987 and 2006 are the most prominent entries in the record of what happened when they were not. But between those two moments, and in the years following them, engineers were building a progressively more detailed understanding of exactly what makes a car carrier behave the way it does. And that understanding eventually produced the systems that define how these ships are built and operated today. The first and most fundamental of these systems addresses a problem that is unique to car carriers among large commercial vessels. The cargo height varies. On a bulk carrier loading grain or ore, every cubic meter of cargo weighs roughly the same, and the weight distribution in the hold is predictable and uniform. On a car carrier, a Voyage might carry standard passenger sedans on some decks, tall SUVs on others, commercial vans on another, and heavy construction equipment or agricultural machinery on the lowest levels. Each of these cargo types has a different height, a different weight, and a different position relative to the ship's center of gravity. A deck loaded with heavy construction equipment sitting low in the hull contributes very differently to the ship's stability than the same deck loaded with lightweight passenger cars sitting high up. The mix of cargo on a given voyage is determined by commercial demand, not engineering convenience, and it changes from voyage to voyage. The solution that emerged from this challenge is one of the most distinctive features of a modern car carrier: movable decks. Unlike virtually every other type of cargo vessel, where the internal structure is fixed at the time of construction, a significant portion of the decks in a modern car carrier are suspended on hydraulic lifting systems that allow them to be repositioned vertically. The range of movement is substantial. A deck can typically be raised or lowered by a meter or more from its neutral position, changing the clearance between levels from a minimum of around 2 meters, sufficient for a standard passenger car, to 3 meters or more, sufficient for a large commercial van or a piece of agricultural equipment. This flexibility serves two distinct purposes. The obvious one is cargo accommodation. By adjusting deck heights, the ship can physically fit a wider variety of vehicle types without wasting space. A deck configured for passenger cars with 2 meters of clearance can hold significantly more vehicles than the same deck configured for tall commercial vans, and the ability to switch configurations between voyages makes the ship more commercially versatile. The less obvious but more important purpose is stability management. By adjusting which decks carry which cargo, and at what height, the ship's operators can influence where the combined center of gravity of the entire loaded vessel sits before it leaves port. Heavy cargo placed low keeps the center of gravity down and improves stability. Light cargo placed high raises the center of gravity and reduces it. The art of loading a car carrier, and it genuinely is an art, practiced by specialized cargo planners using sophisticated software, involves finding the combination of deck assignments, cargo placement, and ballast water loading that produces the best possible stability profile for the specific mix of vehicles on that voyage, in the specific weather conditions anticipated on the route. This planning process was formalized and made more rigorous in the years following the Cougar Ace incident, when the International Maritime Organization updated its stability requirements for car carriers to include more detailed loading plan approvals and pre-departure stability calculations. Before the Cougar Ace, the stability planning for many voyages relied on relatively simple calculations using estimated cargo weights and standard deck configurations. After it, the requirements moved toward more detailed modeling that accounted for the actual distribution of cargo weight across all 12 decks, the interaction between different cargo types at different heights, and the dynamic behavior of the loaded vessel in the sea states expected on the route. But all of the pre-departure planning in the world cannot fully account for what happens once the ship is at sea, because the ocean introduces variables that no loading plan can anticipate. Waves do not arrive at predictable intervals from predictable directions. Wind speeds change. The ship consumes fuel, which shifts its weight distribution. Ballast water may need to be adjusted for reasons unrelated to stability, to maintain the correct trim for fuel efficiency, for example, or to manage the effects of cargo shifting during a storm. A car carrier at sea is a dynamic system, not a static one, and its stability must be managed continuously rather than calculated once at departure and then trusted to hold. This is where the ballast system becomes the central operational tool for stability management, and where the complexity of running a modern car carrier becomes most apparent. The ballast tanks of a large car carrier are not a simple pair of chambers that can be filled or emptied as a unit. They are an interconnected network of dozens of individual tanks, distributed throughout the hull at different positions along the ship's length, width, and depth. The positioning is deliberate. By filling or emptying specific tanks in specific combinations, the ship's operators can shift the center of gravity in any direction, forward or back along the ship's length, port or starboard across its width, and up or down depending on which vertical level of tanks is used. The total ballast water capacity of a large car carrier can reach 40 or 50,000 tons, a quantity that, when distributed across the tank network, gives operators fine-grained control over how the ship sits in the water. The pumping system that moves this water is correspondingly powerful. On a modern large car carrier, the ballast pumps can transfer water between tanks at rates of several thousand liters per second. This is not primarily a matter of efficiency. It is a matter of response time. When a ship begins listing in heavy weather, the rate at which the ballast system can shift weight to counteract the list determines whether the situation is corrected before it becomes dangerous. Naval architect Svein Erik Hansen, whose research on ro-ro vessel stability has been widely cited in the maritime engineering literature, documented that the critical window between the onset of a dangerous list and the point at which it becomes self-reinforcing can be measured in minutes, and that ballast pump capacity is one of the key parameters determining whether that window is wide enough to allow intervention. The Cougar Ace disaster demonstrated, among other things, that this window can close faster than expected when the initial cause of the list is the ballast system itself. The asymmetric draining of tanks during the water exchange procedure created an imbalance that the ship's corrective systems were not fast enough to reverse. One of the procedural changes that followed the incident was a requirement for more conservative sequencing during ballast water exchange, specifically ensuring that the tanks being refilled are brought to their target level before the tanks being drained are emptied below a safe threshold. The change sounds simple, but implementing it correctly requires careful management of the simultaneous operation of multiple pumps across a large tank network, and the software systems used to manage this process were substantially upgraded across the fleet in the years following the incident. Managing the ballast system correctly is, however, only part of the stability challenge. The other part involves the external forces that the ocean applies to the hull, and this is where the physics of car carriers diverges most sharply from other large vessels. The sail area problem that was described in the previous chapter, the fact that car carriers present enormous flat surfaces to crosswinds, has no complete solution. The flat sides are a consequence of the ship's purpose. You cannot make the hull narrower or lower without reducing the number of vehicles it can carry, which defeats the economic rationale for building the ship. What engineers can do is design the hull and keel geometry to maximize the ship's resistance to rolling and add active systems that counteract rolling forces as they develop. The hull geometry approach works through the same principle as a low-slung sports car staying flatter in corners than a tall SUV. By keeping the hull's underwater volume as wide and as deep as possible relative to its above-water volume, designers minimize the ratio between the forces that tend to roll the ship and the forces that resist rolling. The specific cross-sectional shape of a car carrier hull, wider at the waterline than at the keel, with a carefully calculated bilge radius, is the product of decades of refinement in exactly this direction. Svein Erik Hansen's work on ro-ro stability specifically highlighted the importance of this hull form as what he called a passive stabilizer, a structural property that provides a baseline level of rolling resistance regardless of what the active systems are doing, and that crucially maintains some stabilizing effect even at extreme angles of heel where the active systems may have already been overwhelmed. The active systems, the ones that respond dynamically to rolling forces as they occur, come in two forms on modern car carriers, and they work at different timescales. The first form is the anti-roll tank system, which is a refinement of the basic ballast concept. Dedicated tanks positioned at the sides of the ship, connected by large diameter pipes, are partially filled with water. As the ship rolls to one side, the water in these tanks flows toward the low side under gravity, which would normally make the roll worse. But the pipes connecting the tanks are fitted with controlled valves that regulate the flow rate, and the timing of this flow can be tuned so that the water arrives at the low side slightly after the peak of the roll, effectively pushing back against the roll at the moment when corrective force is most useful. The mathematics of this tuning is not trivial. It depends on the ship's natural roll period, which itself depends on the loading condition. But modern computerized systems can calculate and apply the correct settings in real time. The second and more sophisticated form of active stabilization is the fin stabilizer system, which began appearing on larger car carriers in the 1990s and has become standard on new construction since the early 2000s. Fin stabilizers are retractable hydrofoil-shaped fins, each roughly 5 meters in span, mounted in pairs on the hull below the waterline amidships. When deployed, they work like the control surfaces of an aircraft. By changing the angle of attack of each fin, the ship can generate a lifting or depressing force on either side of the hull that directly opposes rolling. The forces involved are substantial. A properly sized fin stabilizer system can reduce rolling amplitude by 60 or 70% in moderate sea states. What makes modern fin stabilizer systems particularly effective is not the fins themselves, but the control system that operates them. In the generation of systems installed on ships in the 1990s, the fins responded to the ship's actual rolling motion. They were essentially reactive, moving to counteract a roll that had already begun. In current generation systems, the control algorithm is predictive. Sensors mounted at the bow of the ship measure the characteristics of approaching waves, their height, period, and angle of approach, and the control system uses this data to calculate the rolling motion that the ship will experience when those waves reach the hull. The fins are adjusted before the wave arrives, so that the stabilizing force is applied at precisely the right moment to prevent the roll from developing, rather than correcting it after the fact. The difference in effectiveness between reactive and predictive control is significant. A predictive system can achieve the same roll reduction with smaller fin movements, which reduces mechanical wear and energy consumption, and it can maintain stability in sea states that would overwhelm a purely reactive system. The October 2020 crossing of the North Atlantic that was mentioned in the previous chapter illustrates how all of these systems work together under real conditions. The vessel involved encountered a deep Atlantic low-pressure system that produced sustained winds above 50 knots and significant wave heights exceeding 15 meters, conditions at the upper end of what car carriers are routinely exposed to. The onboard monitoring systems recorded gyroscopic measurements of hull motion to within 1/100th of a degree throughout the event. The predictive fin stabilizer system made continuous adjustments based on wave data from the bow sensors, averaging several dozen fin position changes per minute at the peak of the storm. The ballast pumps ran continuously, redistributing water between tanks to maintain trim as fuel consumption gradually shifted the ship's weight distribution. The combination of these systems kept the ship's rolling amplitude within acceptable limits throughout the crossing, and the cargo arrived at the destination port without incident. What the October 2020 crossing also illustrated, though it was not the focus of the subsequent reports, is how dependent all of these active systems are on accurate, continuous data about the ship's condition and its environment. The predictive stabilizer control only works if the bow sensors are functioning correctly and the wave prediction algorithm is well calibrated. The ballast management system only works if the tank level sensors are accurate and the pump control logic is correctly implemented. The loading plan only works if the actual cargo weights match the declared weights, a problem that has historically been more significant for car carriers carrying construction equipment and commercial vehicles, whose masses are sometimes understated in shipping documentation. This dependence on data quality and system reliability creates a vulnerability that is different in character from the structural vulnerabilities addressed by hull geometry and fin stabilizers. A structural vulnerability is always there, and its magnitude is fixed by the design. A system's vulnerability can be latent for years, invisible under normal operating conditions, and then manifest suddenly when a combination of factors, sensor failure, software error, unusual cargo distribution, extreme weather, removes the layers of protection simultaneously. The maritime engineering community has been grappling with this category of vulnerability with increasing seriousness since the Cougar Ace incident made clear that the active systems designed to prevent a catastrophic list could themselves become the cause of one. The ballast water exchange that triggered the 2006 disaster was not a failure of the ballast system in the sense of a pump breaking down or a tank leaking. It was a failure in the management of the system, a sequence of operations that individually were correct, but collectively produced a dangerous outcome. Preventing that kind of failure requires not just reliable hardware, but robust procedural design, thorough crew training, and monitoring systems that can detect an emerging imbalance before it develops momentum. All of this complexity, the movable decks, the ballast network, the fin stabilizers, the predictive control systems, the loading plan software, the procedural protocols, represents the industry's current best answer to the fundamental question of how to keep a 15-story floating parking garage upright in the open ocean. It is an answer that has been built incrementally through a combination of deliberate engineering development and hard lessons learned from incidents that revealed where the previous answer was insufficient. But keeping the ship upright is only one part of what these vessels need to do safely. The cargo inside, thousands of cars, packed tightly in enclosed spaces with no ventilation openings to the outside, soaked in fuel vapors and surrounded by flammable materials, faces a threat that the most sophisticated stability management system in the world is completely powerless against. A threat that the industry spent decades believing it understood, and that turned out, in the second decade of the 21st century, to have changed into something that the existing defenses were not designed to handle. Chapter 4. A month in the salt. And not a scratch. Every new car sitting in a dealership showroom has a history that its future owner will never see on the window sticker. If that car was built in Japan, South Korea, or Germany, and is now sitting in a lot in California, Texas, or the United Kingdom, there is a very high probability that it spent somewhere between 2 and 5 weeks crossing an ocean in the hold of a car carrier, exposed to one of the most chemically aggressive environments on the planet, in conditions that would destroy an unprotected metal surface within days. The fact that the car looks factory fresh when it arrives, with paint that shows no trace of what it has been through, is not an accident. It is the result of a protection system that spans multiple industries and multiple stages of the vehicle's journey, and that was developed through decades of expensive failures before it reached its current form. To understand why the marine environment poses such a serious threat to a new vehicle, you need to understand what seawater actually does to metal. Not in the long term, in the way that we think of rust as a slow process, but in the short term, under the specific conditions of an ocean crossing. Seawater is a complex chemical solution containing roughly 3.5% dissolved salts by weight, of which the most significant for corrosion purposes is sodium chloride. When seawater or its aerosol form, the fine mist of salt particles suspended in air near the ocean surface, contacts a steel or aluminum surface, the chloride ions in the salt begin attacking the thin oxide layer that naturally forms on metal surfaces and provides their primary passive protection against corrosion. This oxide layer is only a few nanometers thick, but under normal conditions it is remarkably effective. It forms spontaneously, repairs itself when damaged, and provides a barrier that prevents oxygen and water from reaching the bare metal beneath. Chloride ions disrupt this barrier by chemically displacing the oxide compounds and replacing them with metal chlorides, which are soluble and wash away rather than forming a protective layer. Once the oxide layer is locally compromised, a corrosion pit forms, and the electrochemical process of rusting accelerates around that pit because the disrupted surface creates the electrical potential differences that drive oxidation. The rate at which this process operates depends on several factors: temperature, humidity, chloride concentration, and the presence of contaminants that can catalyze the electrochemical reactions. In the marine environment of an ocean crossing, all of these factors are simultaneously unfavorable. The air inside a car carrier hold is saturated with salt aerosol drawn in every time the cargo ramp is opened for loading or unloading. The humidity is high, providing the electrolytic medium that the corrosion process requires. The temperature fluctuates as the ship crosses climate zones, creating cycles of condensation on metal surfaces that deposit and concentrate salt. And the duration, 3 to 5 weeks, is long enough for significant corrosion to develop on an unprotected surface, even without accounting for the periods of heavy weather during which the hold environment becomes particularly harsh. The first automakers to ship vehicles in volume to overseas markets discovered this the hard way. Early reports from American dealers receiving Japanese cars in the 1960s and 1970s documented a consistent pattern of surface rust on arrival. Not structural corrosion, but visible oxidation on body panels, window frames, and underbody components that had been in contact with the marine atmosphere during the crossing. The problem was not catastrophic in the sense of making the cars unusable, but it was commercially damaging. A car that shows rust before it has been sold is a car that requires reconditioning before delivery, which costs time and money, and that may have already suffered paint adhesion damage that will accelerate corrosion after the customer takes delivery. The initial responses to this problem were pragmatic, but imperfect. Some manufacturers began applying heavier coats of undercoating to vehicles destined for export. Others wrapped vulnerable components in plastic film. Some simply accepted a higher rate of pre-delivery reconditioning as a cost of doing business. None of these approaches addressed the fundamental issue, which was that the painted steel surface of a car body, however well it had been finished at the factory, was not designed to withstand prolonged exposure to marine aerosol without additional protection. The solution that eventually emerged and became the industry standard was the development of transit wax, a temporary protective coating applied specifically for the purpose of ocean shipping. The concept is simple. Apply a layer of chemical protection over the factory paint before the car is exposed to the marine environment, and remove it cleanly after arrival at the destination. The execution is considerably more complex because the coating needs to satisfy several demanding and partially contradictory requirements simultaneously. It must bond strongly enough to the paint surface to resist the physical washing and mechanical abrasion of a rough ocean crossing, including the spray and vibration to which the outer surfaces of vehicles on the upper decks of a car carrier are exposed. It must provide a chemical barrier that prevents chloride ions in marine aerosol from reaching the paint, which means it must be both adherent and impermeable to chloride at the concentrations found in ocean air. It must not react with the paint chemistry beneath it. Some early wax formulations caused lifting or discoloration of certain paint types, particularly metallic finishes, and the chemistry had to be refined considerably before a truly universal formulation was available. And it must be completely and cleanly removable at the destination, without leaving residue that would require additional cleaning before the car reaches the customer, and without damaging the paint surface during removal. The development of transit wax formulations that met all of these requirements took place largely through the 1970s and 1980s, driven by the growing volume of Japanese vehicle exports and the associated commercial pressure to deliver cars in showroom condition. The chemistry that emerged, proprietary in its details, varying somewhat between manufacturers and suppliers, but broadly similar in its approach, uses a combination of microcrystalline waxes, polymers, and corrosion inhibitors suspended in a carrier solvent. When applied to the paint surface and allowed to cure, the wax forms a continuous film that bonds to the paint through van der Waals forces and hydrogen bonding without chemically reacting with it. The corrosion inhibitors in the formulation provide an additional layer of protection by chemically neutralizing any chloride ions that manage to penetrate the wax film before they can reach the paint surface. Application is automated at modern production facilities. After the final paint and clear coat layers are applied and cured on the assembly line, vehicles pass through an application station where the transit wax is sprayed uniformly over all exterior surfaces. The application is metered precisely to achieve the specified film thickness. Too thin, and the protection is inadequate. Too thick, and removal becomes difficult or incomplete. The wax is then allowed to cure under controlled temperature conditions before the vehicle moves to the final assembly area for installation of interior components, fluids, and documentation. At the destination port, removal is handled at the port terminal or at vehicle processing centers operated by the automaker's logistics partners. The standard removal method uses hot water at high pressure, typically around 70 to 80 degrees Celsius at pressures of several hundred bar, applied by robotic wash systems or trained operators using manual equipment. The combination of heat, which softens the wax film, and mechanical pressure, which physically strips it from the surface, removes the coating completely in a single pass over the vehicle. The wash water and dissolved wax are collected and treated before discharge to meet environmental requirements, because the wax formulations contain compounds that would be harmful to aquatic environments if released untreated. After washing, the vehicles are inspected for any paint defects, transit damage, or contamination that the wash process may have revealed. Vehicles that pass inspection proceed directly to dealer preparation. Those with defects are diverted to reconditioning facilities, where paint touch-up, panel adjustment, or other remediation work is carried out. The inspection and reconditioning process is itself a significant operation at major vehicle import terminals, employing hundreds of trained technicians at facilities like the large vehicle processing centers at the ports of Baltimore, Los Angeles, and Rotterdam. Transit wax protects the exterior paint surfaces of a vehicle, but it cannot address every surface. The underside of the vehicle, the floor pans, suspension components, exhaust system, and brake hardware, is not coated with transit wax because it is not accessible to the spray application systems used at the factory. These surfaces are protected by the undercoating applied during production, which is a different formulation designed for long-term corrosion resistance rather than temporary transit protection, and by the fact that the undersides of vehicles are not typically exposed to the direct airflow that carries marine aerosol through the cargo hold. Interior surfaces, door cavities, sill channels, the inner faces of body panels, present a more complex protection challenge. These spaces are enclosed, which means they are not directly exposed to marine aerosol under normal conditions, but they are also difficult to ventilate, which means that any moisture that enters them is slow to leave. If moisture containing dissolved chlorides accumulates in a door cavity or sill channel during an ocean crossing, it can initiate corrosion from the inside of the panel, a form of damage that may not be visible for months or years after the car is delivered, but that has already compromised the structural integrity of the affected component. The primary defense against this form of damage is not a coating, but a climate. If the air inside the cargo hold is kept dry enough, marine aerosol does not condense on interior surfaces, and chloride-containing moisture does not accumulate in enclosed cavities. This is the function of the dehumidification system that is now standard on modern car carriers, and it represents a significant engineering achievement in its own right. Maintaining controlled humidity in a space the size of a car carrier hold, which, across 12 decks, represents an interior volume of several 100,000 cubic meters. While the ship is crossing ocean regions with wildly different ambient conditions presents a formidable technical challenge. The hold is not perfectly sealed. Air enters around ramps, through ventilation intakes, and through any imperfections in the hull closures. Every time a ramp is opened for loading or unloading, a large volume of outside air, potentially saturated with marine humidity, enters the hold. The cargo itself, thousands of cars with their interior volumes, fabric upholstery, rubber seals, and glass surfaces, acts as a reservoir that absorbs and releases moisture depending on the ambient conditions. The dehumidification systems used on modern car carriers are industrial-scale adaptations of the technology used in pharmaceutical manufacturing facilities, food storage warehouses, and other applications where precise humidity control is critical. The core technology is desiccant dehumidification, in which the hold air is drawn through a rotating wheel or bed of desiccant material, typically silica gel or lithium chloride, that absorbs water vapor from the air. The moisture-laden desiccant is then regenerated by passing hot air through it to drive off the accumulated water, which is condensed and drained. The cycle is continuous, and the capacity of the system is sized to maintain the hold humidity below a specified level, typically 40 to 45% relative humidity, even under the most challenging ambient conditions the ship is likely to encounter. The target humidity level of 40 to 45% was not chosen arbitrarily. It is derived from corrosion science research on the critical humidity threshold for atmospheric corrosion of steel. Below approximately 40% relative humidity, the thin film of adsorbed moisture on a metal surface is too thin and discontinuous to support the electrochemical reactions of corrosion. Above this threshold, moisture film thickness increases rapidly with increasing humidity, and corrosion rates rise correspondingly. The 40 to 45% target provides a margin below the critical threshold that accounts for measurement uncertainty and local variations in humidity within the large hold volume. Maintaining this humidity level requires the hull to be well sealed against the ingress of outside air, and modern car carriers incorporate several features specifically designed to achieve this. The large access ramps and cargo doors, which are the primary potential paths for outside air infiltration, are equipped with inflatable rubber seals that expand when the ramp is closed to create an airtight seal against the hull structure. Before departure, these seals are tested using ultrasonic leak detection instruments. A transducer placed inside the hold generates an ultrasonic signal, and a receiver on the outside of the hull is used to detect any points where the signal penetrates, indicating a gap in the seal. Any gaps found are addressed by adjusting the hydraulic pressure on the ramp closure mechanism or by replacing worn seal sections. The ventilation system, which serves both fire safety and climate control functions, is designed with dampers that can close all ventilation openings when the hold is operating in dehumidification mode. When the dampers are closed, the hold is effectively a closed system, and the dehumidification plant operates in recirculation mode, continuously treating the same air volume. When the hold temperature needs to be managed to prevent overheating in tropical climates, or to equalize temperatures when the ship is crossing large climate gradients, the dampers are opened and outside air is introduced in controlled quantities, with the dehumidification system sized to handle the additional moisture load. The monitoring systems that oversee all of this are integrated into the ship's broader environmental management network. Humidity sensors distributed throughout the hold, typically several per deck, positioned to capture the range of conditions that may exist in different parts of the large hold volume, feed data to the central monitoring system continuously. If any sensor detects a reading approaching the upper limit, the monitoring system triggers additional dehumidification capacity and alerts the officer on watch. The data from these sensors is logged continuously throughout the voyage, creating a record that can be reviewed if a dispute arises about the condition of a vehicle at delivery. The entire system, transit wax, sealed hull, industrial dehumidification, continuous monitoring, represents the outcome of several decades of development driven by the straightforward commercial imperative that a car arriving at a dealership needs to be in the same condition it left the factory. What is striking about it, when viewed as a whole, is how thoroughly the solution crosses industrial boundaries. The chemistry of transit wax was developed by coatings specialists working with automakers. The dehumidification technology was adapted from other industrial applications by marine equipment manufacturers. The hull sealing systems were developed by shipbuilders in response to specific operational problems that only became apparent once the ships were in service, and the inspection and reconditioning systems at destination ports were built up by logistics companies operating in the gap between what the ships delivered and what the dealers needed to receive. All of these pieces came together not through a coordinated design process, but through the accumulated pressure of commercial necessity and the gradual sharing of knowledge across an industry that was, in its early decades, learning what it did not know. The result is a protection chain that, when it works correctly, makes the ocean crossing invisible to the end customer. The car arrives, the wax is washed off, and the only evidence that it spent a month at sea is a document in the delivery file that the customer will never read. But all of this protection, the wax, the dehumidification, the sealed hull, only matters if the cars are still in their places when the ship arrives. And whether they are in their places depends on something that has nothing to do with chemistry or climate control, but everything to do with 4 textile straps per wheel, installed by hand by a crew member working in a dark, exhaust-filled hold at the beginning of a voyage that will test those straps against forces no specification fully anticipated. The system that keeps 10,000 cars from becoming 10,000 projectiles during a North Atlantic storm is simpler in concept than anything discussed in this chapter, and considerably more dependent on the skill and attention of a single human being doing a job that most people have never heard of. Chapter 5. 12 seconds per car. Every 12 seconds, a new car rolls down the ramp of a car carrier onto the pier. 300 vehicles an hour, across a shift that runs without pause from the moment the first ramp is lowered to the moment the last car clears the hold. At that tempo, a fully loaded ship carrying 10,000 vehicles can be emptied in just over 30 hours of continuous operation, a rate that the port of Zeebrugge in Belgium, one of the busiest vehicle import terminals in the world, achieves routinely and considers a baseline rather than a peak performance. The number sounds straightforward until you think about what it actually requires. Every one of those 12-second intervals represents a human being getting into an unfamiliar car in a dark, poorly ventilated hold, assessing its dimensions and controls in a few seconds, navigating a narrow corridor between hundreds of other vehicles with centimeter clearances on both sides, descending internal ramps that can be steep enough to compress the car's suspension noticeably, and delivering the vehicle to the correct staging area on the pier without leaving any trace of the journey on the bodywork. Multiply that by 300 times per hour, sustained across a working day with no margin for error on any individual repetition, and you have a job that requires a specific combination of spatial perception, vehicle handling skill, and sustained concentration that is rarer than it sounds and harder to train than it looks. The people who do this work are known in the industry as car jockeys or port drivers, and they occupy an unusual position in the logistics chain that moves vehicles from factory to customer. They are not, in most cases, employees of the shipping company or the automaker. They work for specialist vehicle handling contractors that operate inside major vehicle import ports under long-term agreements with the terminal operators. Their work is invisible to the end customer. Nobody who buys a new car thinks about the sequence of human decisions that got it off the ship. But it sits at the most vulnerable point in the entire protection chain that was described in the previous chapter. All of the engineering effort that went into transit wax, hull sealing, and dehumidification can be undone in a fraction of a second by a car jockey misjudging a gap or catching a door edge on an adjacent vehicle. Understanding how the industry manages this risk requires understanding the environment in which car jockeys work, because the environment itself is the primary constraint on everything they can and cannot do. A car carrier hold is not designed for human comfort or operational convenience. It is designed to maximize the number of vehicles that can be packed into a given hull volume, and the result is a space that feels, to anyone entering it for the first time, simultaneously enormous and claustrophobically tight. The individual decks are low, typically just over 2 meters of clearance for decks configured for passenger cars, and the vehicles are parked in rows with gaps that are precisely calculated to fit as many cars as possible while leaving just enough room for a person to move between them. The lighting is artificial and uneven, supplemented by portable lights when needed. There are no road markings, no directional signs, no lane lines painted on the deck. Orientation inside the hold requires either memorizing the layout from a briefing before entry or following the guidance of marshals positioned at key junctions. The ventilation system that prevents explosive fuel vapor accumulation runs continuously and creates a steady background noise that makes spoken communication difficult. The air smells of exhaust and fuel because hundreds of engines were running inside the enclosed space during loading, and some residual concentration of combustion products always remains. In hot climates, the temperature inside the hold can be significantly higher than outside because the metal structure absorbs solar heat, and the ventilation, while sufficient for fire safety purposes, is not powerful enough to maintain comfortable working temperatures. In cold climates, the steel decks become slippery with condensation. These conditions set the context for every decision a car jockey makes. They are not working in a controlled environment with clear sight lines and ample room for error correction. They are working in a space that demands precise execution from the beginning of each maneuver, because there is rarely enough room to recover from a mistake without stopping. And stopping, as will be explained, has consequences that ripple through the entire unloading operation. The traffic management system inside a car carrier during unloading is built around a single organizing principle: unidirectional flow. Every vehicle moves in one direction only, forward, following a predetermined route from its position in the hold, down through the internal ramps, and out through the main ramp to the pier. There is no provision for reversing, no ability for a car jockey who has made a wrong turn to back up and try again. The internal ramps connect the 12 decks in a sequence that routes vehicles progressively from the highest decks to the lowest, and from the interior of the ship toward the stern ramp, in a flow that resembles water draining through a funnel, controlled, directional, and dependent on each element moving when and where it is supposed to. This design is not merely a matter of operational efficiency, though efficiency is part of it. It is a fundamental safety requirement arising from the dimensions of the spaces involved. The corridors between parked vehicles and the ramps connecting the decks are wide enough for a single vehicle to pass with reasonable clearance on each side. But they are not wide enough for two vehicles moving in opposite directions to pass each other safely. A bidirectional flow system in these spaces would require either much wider corridors, which would reduce the number of vehicles that could be carried, or some form of traffic signal and passing bay arrangement, which would add complexity and reduce the flow rate. The unidirectional solution trades flexibility for reliability. Every car jockey knows exactly which direction traffic flows. There is no possibility of head-on encounters, and the system degrades gracefully under any individual delay because the blockage is simply a pause in the flow rather than a gridlock. The choreography of unloading begins hours before the first car moves, with a detailed briefing for the car jockey team led by the terminal supervisor. The briefing covers the layout of the specific ship. Car carriers vary in their internal configurations, and a jockey who knows one vessel well may find the ramp locations and deck numbering system of a different ship disorienting on first entry, the sequence in which decks will be cleared, the staging areas on the pier to which different vehicle types will be directed, and any specific handling instructions for particular vehicles in the cargo. Some vehicles require special handling, cars with discharged batteries that cannot be started under their own power, vehicles with low ground clearance that require special care on steep ramps, electric vehicles that must be handled with particular attention to the state of their battery systems. The briefing also covers the communication system that will coordinate the operation. In the enclosed, noisy environment of the hold, verbal communication over distance is unreliable, and radio communication is complicated by the metal structure of the hull, which creates dead zones where radio signals do not penetrate. The solution used at most major terminals is a system of light signals. Marshals positioned at key junctions in the hold carry colored flashlights or light wands and use standardized signals to direct car jockeys at decision points, indicating which lane to take at a fork, when to proceed and when to wait, and where to stop if a problem develops ahead. The signals are simple enough to be understood quickly and reliably in poor visibility and under the cognitive load of actively driving a vehicle through a tight space. The pier staging area, where vehicles are parked after unloading, is organized with similar precision. Different vehicle models, trim levels, and destination markets are assigned to specific zones of the staging area, and car jockeys are responsible for delivering each vehicle to the correct zone and positioning it within that zone according to the terminal's parking protocol. The spacing within staging zones is tight. Cars are typically parked within 30 to 40 centimeters of each other, and the parking maneuvers required to achieve this spacing in a consistent, damage-free way are themselves a significant skill. A car jockey who can quickly drive an unfamiliar car through a narrow hold corridor and then execute a precise parking maneuver in a staging area without excessive back and forth is doing something that most ordinary drivers, given the same instructions, would find unexpectedly difficult. The professional preparation required to perform this work reliably is more substantial than the job's public profile would suggest. The selection process at major vehicle handling contractors typically involves a practical driving assessment in which candidates are asked to navigate a vehicle through a course designed to evaluate spatial judgment, throttle and brake control, and the ability to maneuver in confined spaces without reference to the kind of visual cues, painted lines, curbs, bollards, that most drivers rely on. Candidates who pass the initial assessment go through a training period during which they work alongside experienced jockeys in the hold, building familiarity with the specific ships operated at the terminal and the specific vehicle types they will be handling. The range of vehicles that a car jockey may need to handle in a single shift is, at a busy international terminal, very wide. A modern car carrier may carry vehicles from multiple manufacturers, in configurations ranging from subcompact city cars to large pickup trucks, commercial vans, and occasional heavy equipment. Each of these vehicles has different dimensions, different seating positions, different control layouts, and different handling characteristics. A compact Japanese sedan handles very differently from a large American pickup truck, which handles very differently from a European commercial van, which handles very differently from an electric vehicle with regenerative braking that feels unfamiliar to anyone accustomed to conventional cars. A skilled car jockey can assess a vehicle's dimensions and basic handling characteristics within the first few seconds of driving it and adapt their approach to the specific vehicle, adjusting for a longer wheelbase, accounting for a higher seating position that changes the sightlines, managing the different braking feel of a vehicle type they may not have encountered before. The clothing regulations that govern work in the cargo hold are a detail that illustrates how seriously the terminal operators take the risk of damage to vehicles. Car jockeys working in the hold are required to wear clothing with no exposed metal hardware, No belt buckles, no metal buttons, no zipper pulls, no rivets on pockets. Footwear must have no metal components, including the steel toe caps that are standard in most industrial work environments. The reason is straightforward. In the tight spaces of a car carrier hold, a worker moving between vehicles will inevitably brush against bodywork, and a metal button or buckle contacting a freshly painted surface will leave a mark that cannot be polished out. The entire month-long protection chain, factory paint, transit wax, humidity control, dehumidification, can be defeated in a fraction of a second by a belt buckle catching on a door edge. Similarly, car jockeys are prohibited from adjusting any vehicle settings during the unloading process. Seat position, mirror angles, steering column height, audio system settings all must remain exactly as delivered from the factory. This requirement serves two purposes. First, it ensures that the vehicle arrives at the dealer in genuine factory condition, which matters to customers who expect their new car to be untouched. Second, it prevents the accumulation of the small adjustments that each driver makes naturally when getting into an unfamiliar vehicle. Adjustments that take time, disrupt the flow rate, and, if forgotten, leave the vehicle in a non-standard configuration. The rule is simple enough. Touch nothing you do not need to touch to drive the vehicle off the ship. The time pressure under which car jockeys operate is a constant background condition that shapes every aspect of how the work is managed. A car carrier berthed at a terminal is an asset generating very high daily costs. The vessel itself, the port fees, the capital cost of the cargo, and the contractual commitments to deliver vehicles to dealers on specific timescales all create financial pressure to complete unloading as quickly as possible. Terminal operators track unloading rates meticulously, and the data from major terminals like Zeebrugge, Southampton, and Baltimore shows remarkably consistent rates of 250 to 300 vehicles per hour under normal conditions, with the best-performing teams achieving rates towards the upper end of this range consistently across multiple ships and cargo types. Achieving these rates requires not just skilled individual car jockeys, but a coordinated team operation in which every role, the jockeys driving vehicles, the marshals directing traffic, the supervisors managing the staging area, the administrators tracking vehicle identity and destination, functions with the precision of a choreographed sequence. A delay at any point propagates back through the flow. If a staging area zone fills up and vehicles cannot be delivered there, the jockeys who would normally deliver to that zone have nowhere to go, and the ramp backs up, and the flow from the internal ramps slows, and the jockeys on the upper decks have to wait. The buffer capacity in the system is small, and the recovery time from a disruption is long relative to the time it takes for the disruption to develop. The consequences of individual mistakes within this tightly coupled system are asymmetric. Most mistakes are small and recoverable. A jockey takes a wrong turn and has to stop while a marshal redirects them, costing 30 seconds. A vehicle is parked slightly outside its assigned zone and has to be repositioned, costing a minute. These small delays accumulate and reduce the overall rate, but they do not cause lasting damage. The mistakes that cause lasting damage are physical contact events, a car jockey misjudging a gap and touching an adjacent vehicle, even lightly. A light contact between two vehicles at low speed will typically leave a small paint transfer or a shallow pressure mark on one or both vehicles. Either of those defects, if present on a new car, requires remediation before the vehicle can be delivered to a dealer, which means a trip to the reconditioning area, an assessment by a damage inspector, and repair work whose cost may be relatively small for a minor mark, but whose administrative overhead, documentation, negotiation between the terminal operator and the shipping company about liability and potential delays in delivery is disproportionately large. For this reason, the damage rate, The number of vehicles per thousand unloaded that receive some form of physical damage during the unloading operation is one of the most closely tracked metrics in the vehicle logistics industry, and the commercial pressure to keep it low is intense. Industry data from major terminals suggests that best practice operations achieve damage rates below 1 per 1,000 vehicles, meaning fewer than 1 in 1,000 cars receives any damage during unloading. Achieving this rate consistently while maintaining the flow rates described above is the central performance challenge of the car jockey's work. The tension between speed and precision, moving fast enough to keep the flow rate up while being careful enough to avoid any contact, is resolved differently by different car jockeys, and the variation between individuals is one reason why terminal operators invest significantly in training and performance monitoring. An experienced car jockey does not consciously perceive this as a tension. Through repetition, the spatial judgments become automatic enough that precision and speed are not in conflict. A less experienced jockey may feel the tension acutely, and the temptation to slow down to ensure clearance or to speed up to recover time after a delay is a source of both the caution that prevents damage and the errors that cause it. When the last car has been driven down the ramp and the hold is empty, the car carrier's commercial relationship with its current port is essentially complete. But the ship's relationship with its cargo does not end at the bottom of the ramp. Thousands of vehicles are now sitting in a staging area, waiting to be loaded onto trucks and trains for delivery to the dealer networks across the country. And every one of them was secured to the ship's deck for the duration of the crossing by the system of lashing straps described at the end of the previous chapter. Whether those straps were installed correctly, whether they held throughout the voyage, and whether any vehicle shifted in its position during the crossing are questions that the unloading process will answer, sometimes in ways that reveal vulnerabilities in the securing system that were not apparent when the voyage began. Chapter 6. 4 Straps that Hold Everything. In January 2015, the car carrier Hoegh Osaka departed the port of Southampton on what should have been a routine crossing to the Middle East. The vessel was carrying 1,400 vehicles, including passenger cars, vans, and a number of pieces of heavy construction equipment. The ship had been loaded, cleared by port authorities, and released for departure in the normal way. Less than an hour after leaving the berth, while still in the Solent, the narrow stretch of water between the English mainland and the Isle of Wight, the Hoegh Osaka began to list. The list developed rapidly, reaching a critical angle within minutes. On the car decks, a heavy JCB construction loader had broken free from its lashings and was sliding across the deck, pulling adjacent vehicles with it as it moved. The captain made the decision to deliberately ground the ship on a sandbank called Bramble Bank, rather than allow it to capsize in a busy shipping lane. The vessel came to rest at an angle of approximately 52 degrees, visible from the shore, listing so severely that its hull was partially exposed above the waterline on the high side. Nobody died. The crew of 25 was evacuated successfully. The ship was eventually refloated after several days of salvage work and towed to a dry dock for repairs. But the Hoegh Osaka incident did something that the Cougar Ace incident 9 years earlier had not quite managed to do. It demonstrated, in a setting close to a major port and in full view of the public and the maritime authorities, exactly how quickly and completely a car carrier could be destabilized by the failure of a single securing arrangement on a single piece of heavy cargo. The investigation conducted by the United Kingdom's Marine Accident Investigation Branch concluded that the immediate cause of the list was a combination of factors. The ship had departed with insufficient ballast for the cargo configuration it was carrying. The stability calculations submitted before departure contained errors, and the lashing arrangements for the heavy construction equipment on board were inadequate for the dynamic loads that even moderate sea conditions would impose. The loader that broke free was not improperly secured in a gross sense. It had lashings, they had been installed, and the installation had been checked. What the lashings were not adequate for was the combination of the ship's reduced stability margin and the forces generated by a loaded vessel making a turn in a moderate sea state. When the loader began to move, its weight, several tons, positioned high on the cargo deck, shifted the ship's center of gravity rapidly enough that the ballast system had no time to compensate, and the cascading failure of adjacent vehicles being pushed by the moving loader accelerated the process further. The Hoegh Osaka joined a list of incidents that collectively define why the securing of cargo on car carriers is one of the most technically demanding and consequential operations in the entire logistics chain that moves vehicles from factory to customer. Understanding that chain, the engineering behind the lashing systems, the training of the people who install them, the standards they are supposed to meet, and the ways in which those standards have developed and continue to develop requires going back to the beginning of the Ro-Ro era and tracing how the industry's understanding of the securing problem has evolved over 6 decades. When the first Ro-Ro car carriers began operating in the late 1960s, the securing of vehicles on board was treated as a relatively straightforward, practical matter. Cars were small, light by comparison with other types of cargo, and parked on flat decks. The standard approach was to use simple rope or chain lashings passed through the vehicle's tow hooks or tie-down points, with tension applied by hand. The number of lashings per vehicle, their angle, and the tension they were set to were matters of practice and convention rather than formal engineering analysis. Different shipping companies did things differently, different ports had different standards, and the men who installed the lashings learned the job by working alongside experienced colleagues rather than by following written technical specifications. This informal approach worked reasonably well as long as the ships were small. The cargoes were predominantly light passenger cars, and the routes were relatively sheltered. As the ships grew larger through the 1970s and 1980s, as the cargo mix expanded to include heavier vehicles and equipment, and as the routes extended to include passages through the North Atlantic and the North Pacific, 2 of the roughest ocean regions in the world, the informal approach began to produce failures. Vehicles shifted in heavy weather, causing damage to bodywork, and, in more serious cases, contributing to cargo-induced stability problems. The lashings that had worked adequately on small ships in moderate weather were not adequate for the forces generated on large ships in severe conditions. The response was the development of formal lashing standards, driven primarily by the classification societies, organizations like Lloyd's Register, Bureau Veritas, and DNV, that certify the seaworthiness of commercial vessels and whose approval is required for ships to operate commercially in international trade. The classification societies developed detailed requirements for the design and installation of vehicle securing systems, specifying the minimum braking strength of lashing straps, the number of lashings required per vehicle based on the vehicle's weight, and the ship's stability characteristics, the angles at which lashings should be installed to provide effective restraint in multiple directions, and the tension levels that should be achieved and verified during installation. These requirements were codified into the Classification Society rules and, subsequently, into the guidelines published by the International Maritime Organization under the Code of Safe Practice for Cargo Stowage and Securing. The IMO Code, first published in 1991 and subsequently updated, provides a comprehensive framework for calculating the forces that lashings must resist under the sea conditions and ship motions expected on a given route, and for verifying that the lashing arrangements installed on board provide adequate restraint against those forces. The code is not directly mandatory under international law. Compliance is enforced through the Classification Society rules and flag state regulations of individual countries. But in practice, compliance with the IMO code is effectively universal among reputable shipping companies operating internationally. The engineering basis of the IMO lashing standards is worth understanding in some detail because it reveals both the sophistication of what has been achieved and the inherent limitations of what any standard can guarantee in the face of real-world variability. The forces that a lashing must resist come from two sources. The first is the static weight of the vehicle. Even on a perfectly flat, stationary deck, a lashing must be able to support the vehicle's weight without elongating to the point where the vehicle can slide. This requirement is straightforward to calculate and provides a baseline for the minimum strength of lashing materials. The second source is the dynamic forces generated by ship motion. As a car carrier rolls, pitches, and heaves in response to waves, the vehicles on board are accelerated in multiple directions simultaneously. At any given moment, a vehicle may be experiencing a combination of lateral acceleration from rolling, longitudinal acceleration from pitching, and vertical acceleration from heaving, and the lashings must resist the resultant of all these accelerations simultaneously. The magnitude of these accelerations depends on the ship's motion characteristics, which depend in turn on the ship's size, loading condition, and the sea state being encountered. A large, heavily ballasted ship in moderate weather generates relatively small accelerations. A smaller, lightly loaded ship in severe weather can generate accelerations that impose forces on the lashings several times larger than the static weight of the vehicle. The IMO code specifies the design accelerations that lashing systems must be designed to resist based on the ship type, route, and position of the cargo within the ship. Cargo on upper decks experiences higher accelerations than cargo on lower decks because the ship's rotational motion amplifies with height above the center of rotation. What the IMO code cannot fully account for is the interaction between different cargo items when one of them breaks free. The Hoegh Osaka incident illustrated this limitation clearly. The individual lashings on the JCB loader were calculated to resist the forces generated by the ship's normal motion. They were not designed to resist the additional forces generated by the loader beginning to slide on a deck that was simultaneously losing stability because the loader was sliding, a self-reinforcing dynamic that the static lashing calculation could not capture. Once the loader began to move, its weight, several tons of dense steel machinery positioned well above the ship's center of gravity, was acting as a destabilizing pendulum, and each increment of movement made the stability situation slightly worse, which increased the ship's rolling motion, which increased the forces on the remaining lashings, which caused more of them to fail. The cascade was rapid and essentially uncontrollable once it began. The practical lashing system that has evolved to meet the IMO standards uses synthetic fiber straps as its primary securing element. Modern lashing straps are manufactured from high-tenacity polyester fiber woven into flat webbing of widths, typically ranging from 50 to 75 millimeters. The breaking strength of standard automotive lashing straps is typically in the range of 4 to 6 tons, providing a substantial margin above the forces generated by the vehicle's weight alone. The straps are fitted with ratchet tensioners that allow the installer to apply and verify a specified pre-tension, typically several hundred kilograms, which ensures that the strap is taut enough to prevent any initial movement of the vehicle before the strap begins to carry load. Each vehicle is secured by a minimum of 4 straps, 2 per axle, running from anchor points on the deck to standardized lashing points on the vehicle's understructure. The lashing points, reinforced brackets welded to the vehicle's frame at specified locations, are defined by international standards and are present on virtually all modern vehicles sold in markets where ocean shipping is part of the distribution chain. The angle at which the straps run from the deck anchor point to the vehicle lashing point is critical. A strap running at a shallow angle to the deck is effective at resisting lateral forces, sliding, but less effective at resisting vertical forces, the vehicle being lifted and dropped in heavy heaving motion. A strap running at a steeper angle is better at resisting vertical forces, but takes up more deck space. The standard installation angles specified in the IMO code represent a calculated compromise between these competing requirements, chosen to provide adequate restraint against the combination of forces that the vehicle will experience in service. The installation of lashings is performed by the stevedoring crews who load vehicles onto the ship during the loading operation, and the quality of their work is the final and most variable element in the entire securing system. Well-designed straps, correctly specified anchor points, and detailed IMO-compliant installation instructions are all necessary conditions for adequate securing, but none of them guarantees the outcome. What guarantees, or fails to guarantee, the outcome is whether the individual stevedore installing each strap actually installs it correctly, at the right angle, with the right pre-tension, connected to the right lashing points, free of twists or kinks that would reduce the strap's effective strength, and with the ratchet tensioner properly locked so that the tension cannot relax during the voyage. The conditions under which this work is performed are, as the previous chapter described in the context of car jockeys, not favorable to meticulous attention to detail. The loading operation proceeds rapidly. The commercial pressure to minimize turnaround time is as intense during loading as during unloading, and the stevedoring crew may be installing lashings on hundreds or thousands of vehicles over the course of a loading shift, in a poorly lit, poorly ventilated hold where the noise of running engines makes communication difficult. Fatigue, time pressure, unfamiliarity with specific vehicle types, and the physical difficulty of accessing the lashing points on some vehicles, particularly those with low ground clearance, where the installer may need to lie on the deck to reach the underframe attachments, all create conditions in which errors are more likely than they would be in a controlled, unhurried environment. The supervision and verification systems that exist to catch these errors vary considerably between ports and operators. At well-run terminals with rigorous quality management systems, each vehicle's lashing installation is checked by a supervisor before the vehicle is accepted as secured. The strap angles are verified, the pre-tension is measured with a calibrated gauge, and the ratchet lock is confirmed to be engaged. At less well-run terminals, the checking is more cursory or may rely on the installer's self-reporting rather than independent verification. The investigation into the Hoegh Osaka incident found that while the lashing arrangements had been checked before departure, the checks had not identified the specific inadequacy in the loader's securing arrangement, partly because the inadequacy was not a gross defect visible to a quick inspection, but a subtler mismatch between the specified lashing configuration and the actual load distribution of the particular machine being secured. The heavy equipment problem that the Hoegh Osaka incident put in sharp focus has driven specific improvements in how non-standard cargo is handled on car carriers. Passenger cars, because they are manufactured in standardized configurations with defined weights and standardized lashing points, are relatively straightforward to secure correctly once the installation procedures are established and the stevedoring crew is trained. Heavy construction equipment, agricultural machinery, military vehicles, and other non-standard cargo present a different challenge. Each machine may have a unique weight distribution, non-standard or even absent lashing points, and handling characteristics that the stevedoring crew may have little experience with. For this category of cargo, modern practice at major terminals involves pre-voyage engineering review of the specific securing arrangement by a qualified naval architect or cargo securing specialist who verifies that the proposed lashing configuration can resist the expected forces for the specific machine's weight and geometry. This review is now required by many classification societies for heavy or non-standard cargo, and its implementation has become one of the more significant improvements in car carrier safety practice since the Hoegh Osaka incident. the Cougar Ace incident of 2006 and the Hoegh Osaka incident of 2015. Together define the two ends of the securing problem spectrum. The Cougar Ace showed what can happen when the ship itself becomes destabilized through a system failure and revealed, unexpectedly, that the securing system can hold under conditions far beyond its design specifications if the installation quality is high enough. The Hoegh Osaka showed what can happen when the securing system itself fails and demonstrated how quickly a single failure in the wrong location can cascade into a catastrophe that no level of shipboard automation can prevent once it begins. Between these two demonstrations lies the everyday reality of car carrier operations. Ships crossing oceans with thousands of vehicles secured by 4 straps each, managed by computers that can predict wave impacts and adjust stabilizer fins in milliseconds, crewed by professionals who have trained for years to manage these specific systems, but ultimately dependent on the quality of work done by an individual. Stevedore on a specific strap, on a specific vehicle, at a specific moment during a loading operation that was, by the standards of the port, unremarkable. When a car carrier completes its loading operation and the last ramp is raised and sealed, the ship carries with it the accumulated outcome of every decision made along the chain that brought those 10,000 vehicles to this point. The engineers who designed the hull geometry and the stability systems, the chemists who developed the transit wax, the shipbuilders who installed the dehumidification plant and the fin stabilizers, the cargo planners who calculated the loading sequence, the stevedores who installed the lashings, and the car jockeys who will drive the vehicles off at the other end. All of these contributions, technical and human, automated and manual, engineered and practiced, will be tested simultaneously by the same ocean, on the same voyage, with no opportunity for revision or correction until the ship arrives at the next port. The ocean does not distribute its tests evenly. Most voyages are uneventful, and the elaborate systems described in this story spend most of their operating lives running well within their design envelopes, never approaching the conditions that their margins of safety were calculated to handle. But occasionally, in a North Atlantic winter, in a Pacific typhoon season, in the waters off the Aleutian Islands in July, the conditions arrive that reveal whether the margins were sufficient, whether the systems were maintained correctly, whether the lashings were installed with the care the specifications required. In those moments, the question of whether 10,000 cars arrive intact or become wreckage is answered not by any single decision or any single system, but by the cumulative quality of everything that was done, or not done, from the factory floor to the cargo hold. A note from the author. This video represents several weeks of research across more than 200 sources: maritime accident investigation reports, International Maritime Organization technical documents, academic papers on vessel stability and lithium-ion battery fire chemistry, industry publications, and the records of specific incidents that shaped the regulations and engineering practices described here. The sources span 4 languages, and some of the most useful material, the detailed technical analyses of the Cougar Ace and Hoegh Osaka incidents, exists primarily in the specialized literature of naval architecture and maritime safety, where it is read by professionals and largely unknown outside the industry. What kept drawing me back into this material across weeks of reading was something that is easy to miss when you look at car carriers from the outside. They appear to be simple machines doing a simple job, moving cars from one place to another, and their sheer size makes them seem impersonal, industrial, remote from any human story. But every system on these ships, every regulation governing how they operate, every improvement in lashing standards or suppression technology or stability management has a specific origin in a moment when something went wrong, when people died or cargo was destroyed or a ship was lost. and the industry had to confront the gap between what it had assumed was safe and what had turned out not to be. The rubber gaskets on the cargo ramps exist because 193 people drowned in the water off Zeebrugge in 90 seconds. The predictive stabilizer control systems exist because a ship lay on its side in the Aleutians for 3 weeks, and the questions that raised about how well engineers actually understood these vessels drove a decade of research. The evolving protocols for electric vehicle fire suppression exist because 2 ships burned for 2 weeks in the Atlantic, and nothing in the existing fire safety system could stop them. Every layer of protection that these ships carry was built on top of a failure, by people who decided that the failure should not be allowed to happen again. That process, failure, analysis, improvement, repeated, is how engineering actually works in practice, as opposed to how it appears in retrospect, when the improvements are in place and the failures that necessitated them are history. Car carriers are a particularly clear example of it because the industry is young enough and the ships are distinctive enough that the lineage from specific disasters to specific design features is traceable. The ships sailing the ocean today are, in a very direct sense, built from the lessons of the ships that got into trouble before them. And the ships that will be built in 10 or 20 years will incorporate lessons from the Fremantle Highway and the Felicity Ace that are still being worked out in the IMO working groups and the research laboratories and the engineering offices. Right now, that is what I find worth knowing about these vessels. Not just the engineering, though the engineering is genuinely remarkable, but the human process behind it. The fact that every time the ocean found a weakness, someone spent years figuring out how to eliminate it. The fact that the car sitting in your driveway, if it was built overseas, completed a journey through one of the most hostile environments on Earth and arrived without a scratch because people you will never meet made thousands of decisions over decades to make that possible.